We're going to be talking about Globus Connect and the networking requirements and ways to performance tune it. It's a little bit heavy on the requirements part because I think that when that's understood, it's a lot more obvious how the performance options can affect it. Okay, so a quick review. I just want to establish some terms. I assume that this audience is familiar with these, but I think it will help to separate some confusion that sometimes happens between endpoints and nodes. So this is a slide that's in our presentations for Globus Connect architecture. I'm not going to get super deep into it, but I want to talk about endpoints and nodes a little bit and how those abstractions work in terms of affecting the networking requirements. So an endpoint is really just an abstract concept for the purposes of any kind of network connectivity. It does have a DN name assigned to it and some resources associated with it in Globus Transfer. However, it's a front to the hardware resources like compute, networking, via nodes behind it that are actually where the networking requirements come into play. There's two types of endpoints. We have Globus Connect Server, which is the beefier one, multi-user Linux systems installed typically in a static location, and then Globus Connect Personal, which is your kind of one-click configuration-free installation targeted more at workstation laptops. Get into them in a little bit more detail in a second. So then the nodes, that's what's doing the actual work behind the endpoint abstraction, and that's where the network configuration requirements come into play. So what a node needs in terms of connectivity, it needs to be able to be contacted by Globus services when Globus services need to talk to it. So an out-of-band type request in order to request transfers, explore file systems, do tasks like that. And it forms a control channel in order to communicate that information. It also needs to be able to contact Globus services when it needs to, so on its demand, to do things like register its IP address with the endpoint's DN, get configuration updates, those kind of things. And of course, it needs to connect to its transfer peer. So if it's sending, it has to have a connection with its receiver. If it's receiving, it has to have a connection with the sender. And that's the data channel over which the file information flows. Okay, so Globus Connect Personal. Again, this is targeted at personal computers, laptops. The assumption is that it's going to be behind a firewall, probably a NAT machine. It's going to move around. You're going to put it on your laptop, take it to a coffee shop, take it to the office, take it to work. We can make no assumptions that the network it was on is yesterday is the network it's on today, or that we can control the network that it's on. The only assumption that we make is that it does have outgoing connectivity in terms of active TCP connections, but no incoming connectivity is assumed. So on the other hand is Globus Connect Server. So this is the multi-user installation. There are many nodes backing, or can be many nodes backing an endpoint for horizontal scalability, failover, those kind of things. It is assumed to be in a static position on a network where there is some access to configuration, via cloud services or via a networking operator, something of that nature. It has, because of that network configuration, we can assume that our faster protocols can run on it. Okay, so control channel establishment. So how does that actually work? So for Globus Connect Server, Globus services have to be able to connect to port 443 to form the control channel. So if there is a firewall, that port has to be open for connectivity from Globus services, and also from other clients and other services come into play there too that all connect to 443. GCS itself needs to be able to connect outgoing to port 443 on Globus services. And if you're running any kind of premium connectors or cloud service storage systems that GCS is a front to, it needs obviously to connect to those. So, if GCS has a S3 connection, GCS needs to be able to connect to S3 for obvious reasons. And those are typically on port 443 also. So Globus Connect Personal control channel is an interesting case. So as I mentioned, there's no incoming connectivity that we can assume with Globus Connect Personal. However, as mentioned, Globus needs to contact it whenever Globus needs to. GCP has no idea when that will be. So the way that we solve that problem is there's an SSH tunnel that runs when Globus Connect Personal is running and tries to stay up the whole time, connecting from the network, from the device where Globus Connect Personal is running to Globus Transfer Services. And it runs an SSH tunnel, which is a pretty common thing. I'm sure many people have heard of that. And what it does is it just tunnels the connection. So there's a listener, a TCP listener on the Globus services side that when connected to activates on the other side and looks just like a local connection to Globus Connect Personal. So that's how that control channel is established and how we're able to signal it through a firewall. So the different types of endpoints are important because they affect each endpoint talking to the other type has different characteristics. So these are the important ones, like GCS to GCS, GCP to GCP, and GCS to GCP in both directions there. And we'll talk about each one of those because they're slightly different. Okay, so this is the notation I'm using in the talk. The black arrow is the direction of connection establishment, and the big green arrow is the direction of data flow. Now, while they are pointing in the same direction often, they don't have to be for any reason. You can connect one way and send data the other way. And this will be the notation I use to illustrate this as we go through the talk. Okay, so GCS to GCS. In this case, again, this is the case where we assume some control over the network. Any receiving GCS node, in order to form data channels, must have an open port range for listening, for TCP listeners. By default, it's 50,000 to 51,000. That is configurable, but that's the default. The sender is always the connector. So the listener needs to have that port range open and the connector will connect to it. Parallel streams, I'll talk about that in the performance part, are formed. So you see there's multiple arrows here. Many logical TCP connections are formed over which the data flows. That is called our Mode E protocol in grid FTP nomenclature. So, and it's just a performance enhancement. Oh, whoops. Okay, so GCP to GCP. This one's a fun one. I really like this. So like I mentioned, GCP endpoints are firewalled off behind NAT boxes. You do not control the network, yet they need to form connections with each other. We can't really do the same SSH trick because we don't know who they're going to be sending data to. However, there are some fun magical protocols, Stun and ICE, they're called, which can work with UDP. And I'm not going to get into the details of how they all work, really, because that's a talk in and of itself. But it is fun and interesting, and I have a link in the reference section about it. Really what happens is via sending outgoing UDP packets through stateful firewalls and NAT boxes allows those firewalls and NAT boxes to record that source information, and it makes assumptions that data is going to flow back into those locations, which allows you to, it's not really a trick, but it's, kind of magic, which is why I have that little magic wand right there. And they rendezvous in the middle is a conceptual way to think about it. It's not at all what happens, but it is conceptually solid. Once that connection is established, data can then flow in either direction. And it can use parallel streams in Mode E. This is a slight caveat to what I said before about Mode E having to have the sender be the connector. In this case, they're both kind of the connector, so it's still true that the sender is the connector, but it's a little bit of a caveat for this case. Okay, so GCP to GCS, that's pretty much the same thing as GCS to GCS because, again, you can't connect into GCP, but GCP can connect out. And since GCP is the sender and GCS wants the sender to connect, GCS again has to have this port range open or a port range open, this being the default. GCP can connect out, form parallel TCP streams, send data over them via MODI in our fast protocol. Okay, so GCS to GCP is the problem child case. So the problem here is that for our fast grid FTP protocol MODI, we want the sender to connect, but the sender cannot connect because there is an unconfigurable firewall there. However, GCP can connect out to GCS. So that's how we do it. So GCP connects to GCS, and then data flows back in the opposite direction. The downside here is that it can't use MODI, it can't use parallel streams. We use just mode S, which is simply unframed TCP connection, and there can be a little bit of overhead on checking it. It's not going to be quite as fast. So in this case, if you expect to be receiving a lot of data and you can use GCS, it's probably going to be a better option for you. Okay, so given those requirements, let's talk about restricted network. So I said the ports had to be open, and it's going to be better usability for users if they're open to everyone, but it doesn't necessarily have to be. So the data channel ports, port 50,000 through 51,000, they only need to be contacted by any IP address that's sending you data. So if you want to limit that to a set, you can, but then again, of course, those will be the only ones that will be allowed to connect and send data. Users will still be able to explore others, so they'll get weird errors if it is limited in that way, but it is an option. And similarly, of course, the sender has to be able to form outbound connections to anything it wants to send to. If you want to restrict that by IP, you can, but again, it comes with those caveats. For the control channel side, you can restrict port 443 to our Globus services, which we'll be contacting in. We can provide those IP addresses. And again, outbound, you need to be able to connect to Globus services. And the premium connectors, like I mentioned about S3 or Google Drive or whatever else, like if you're running that type of storage system, obviously you need to be able to connect to it. The last one that's interesting is the access to our package repos. So we have a really convenient command when you're setting up a node behind an endpoint, Globus Connect Server node setup, I believe it's called. And it will reach out to our package repos and download RPMs or debs or whatever you're using and install it and set it all up nicely, which is great. You are going to want to have to allow that connection as well. So to those IP addresses, you don't strictly have to. You could set that up yourself. You could download them somewhere else and bounce them around the network to get them in there. But it's not going to be a great user experience. Better to open up the communication to those as well. Okay, so performance tuning. So to start with, let's take the last one first. So ESNet. To really get performance out of your network, you're going to have to get below our software. And that link right there has all the information you need to tune your network. It'll talk about jumbo frames, various other things, monitoring. They have it all. Get that network path as fast as possible, and then our software can use it optimally. The two knobs that we offer you are parallel streams and concurrency. So parallel streams, I've talked about them a little bit so far, but basically it's the underlying logical TCP connections that we will stripe the data across that we send, and it causes some performance enhancements that I'll talk about in a second. And then concurrency, the number of transfers in progress at one time. I'll get into that as well. So parallel streams, the main thing that it does is it mitigates the effects of packet loss. Packet loss isn't always due to congestion. When it is due to congestion, it's pretty much legitimate. You should go slower, but sometimes routers just get busy for other reasons. Sometimes packets get corrupted and you lose a packet, which can affect overall performance, and parallel streams minimizes or mitigates this a bit. It also will, though, allow for better CPU utilization, particularly in the multi-core world that we're in now. One stream, as we're putting data into streams, Some can be in IO and some can be in scheduled against a CPU, and you can get better stack utilization by using parallel streams. As I mentioned here, the sender does have to be the connector for this to work. So that should work in all cases except for the GCP to GCS case. Sorry, the other way around, GCS to GCP. And it's best for large transfers. So there is some overhead in establishing these parallel connections. And if you're going kind of crazy and have 128 of them and then sending a 1 kilobyte file over it, the signal to noise there is not going to be favorable. So that's something to keep in mind. Okay, concurrency. This whatever this is, this image was surprisingly difficult to make, so I hope everyone loves it. But concurrency is effectively multiple transfers at once. So, let's say you're sending 10 files and you have a concurrency of 5. Well, first, let's say you have a concurrency of 1. That would be send file 1, file 1 is done, send file 2, file 2 is done, send file 3, etc. If you have a concurrency of 5, it will open up 5 separate control channels and send 5 separate requests all at once. As one finishes, it will send the next one. So there'll always be 5 in flight until your data set is fully transferred. And what that does is it allows for some overlap between the requesting phase of any given transfer and the payload phase of any given transfer. And that's what I'm trying to show here. So the low signal is when we're asking for a file to be transferred, and the high signal is when it's being transferred. And as you have more concurrency, you're going to get better overlap and better utilization of the actual data. So here I'm just showing 2, but as you have more, that'll fill in a little bit better up until a point where you can have some thrashing. It's mostly helpful when you have many small files because you're doing a lot of, so the time for requesting and the time for sending, the closer they get together, the more important concurrency is. So, for example, if you're spending 10 milliseconds establishing the request and 10 milliseconds sending it, this is going to look more like a square. But if you're, sending a 10 gigabyte file, the request phase is pretty minimal in terms of payload. So mostly important when you have a lot of small files. When you're thinking about these tuning parameters, here are some things to think about. Is your data partitioned into a ton of kilobyte files or low megabyte files, or is it in gigabyte files? Is it a lot of small files or is it big files? Small files, concurrency is a good thing to look at to help that out. Is it on a wide area network? Is the latency between the 2 endpoints? That's more what I mean than on a wide area network. If the network between the 2 endpoints has high latency, parallel streams affect that more. The penalty for dropping a packet on a WAN is so much worse than on a local area network. So parallel streams really kind of shine in that, but they do help on a local area network as well. That's kind of case by case. A really important thing to consider is the type of connector that you're using. So if the storage system you're backing is just a POSIX regular file system or HPSS or S3 or Google Drive, there's all different characteristics for each one of those, and you want to think about those things. So, for example, can it handle out of order data? Well, POSIX can handle that pretty well. It can seek around a file, no problem. HPSS tape system, not as well, right? Parallel streams necessarily put things out of order. Your data is going to arrive at the receiver in chunks throughout the file, out of order. So there's going to be a bit of seeking there. I mean, we have things to mitigate that, but it's still something to consider. Another is, does the storage system throttle you back? An example, let's take S3 versus Google Drive. So in S3, if you're going to do like a concurrency of 128, something fairly large like that, Amazon's going to happily accept all of your connections and charge you for them, and you can send all of those at the same time without much of a problem. Something like Google Drive, you're going to try to make 128 connections, and I'm not sure this is the correct number, but let's say after 8, it says, hey, the same user just keeps connecting. We're going to send them an HTTP 429 and say, hey, come back later. So now that high concurrency is actually hurting you. Globus will still get your file there. We'll keep retrying until we get it, and we're going to get it there eventually. But that back off phase is going to affect your overall performance. And if you had a lower concurrency, it would have been faster. And then you tape systems like the HPSS. Out of order and concurrency can hurt that at a certain phase, because if there's too many going on at once, there can be some tape contention in the whole system, and it doesn't love to be out of order. So you can set these options, our two main things of concurrency and parallelism, on the endpoint. So again, remembering endpoints have associated with them storage gateways and data nodes. Each data node can have multiple storage gateways. Storage gateways are the connector type effectively. So one endpoint could have S3, Google Drive, HPSS, and POSIX. And as we just discussed, they have very different performance tuning characteristics. So in this case, you can only set it over the entire endpoint, which is not ideal, because you could turn up concurrency very high for POSIX, and then that'll also be very high for Google Drive, and then that's not ideal. However, luckily, we now can set those on the storage gateway. This is a pretty new feature. You can only use the CLI to set it right now, but it's still very convenient. Our standard admin tool, Globus Connect Server, allows you to set it. People pretty much use that when they're setting up data nodes. So it's there, and now you can set these parameters on the storage gateway type, which effectively is a connector type, and tune your endpoint to those specific needs. So instead of it being a one-size-fits-all, you can set it on each endpoint. Okay, and that's all I have. I have some references here, just things I looked at during the talk. The most interesting of which is probably the CSNet one, if people want to look at it.